Second, and that's great. So yeah, so Sander DAHMEN, who's going to talk about interactivity.
All right, well, thank you very much. It's a pleasure being here. So yeah, since it's Monday morning, and apparently some people are still hiding for the rain, we'll take it easy the first hour. But after that, you should be should have woken up, and then it's time to actually get your hands dirty and also work with Lean yourself already. So I think this picture is quite funny. It's actually about computer assistance for the modern novelist, and it's quite old. I don't know. I forgot to look up from when it is, but it's definitely from before ChatGPT. OpenAI released the first version of ChatGPT, and by now it's pretty accurate. 2025. I made some revisions to our novel. Let me know what you think. I don't know if you can read all the rest, but but this is about let's say writing text, and it's quite old, but it's very funny how sort of accurate it is. I think back then it was really a joke, like this will never happen. You can also start talking about mathematics. Can computers do mathematics? And if you let's say change writing a novel by doing research mathematics, then we're certainly not there yet. We're way behind. But maybe this will happen in the future, that computers really can do non-trivial mathematics. And it would be very handy if that there's some nice controlled language which is very precise, in which you can write your mathematics. So you can start to formalize mathematics. And then, we're getting into the different ways you can do that soon. But let me first. Now my button stopped working. No. Okay. All right. But before we get into more details, let me just first give an overview of this course. So I'm teaching it together with Alain, sitting over there. Going to do the second hour. So this hour, as I said already, is just it's Monday morning. So I could have jumped right into Lean. Said, okay, we're going to do Lean, and we're going to do all kinds of syntax and explain some things and do things yourself. Then you would have gotten a little bit further with Lean at the end of this course. But I think it's also good to give sort of a more general perspective of what is formalization about, what has been done in the past. There are also other ways you can formalize, not just with Lean, but with other programs. So we'll do sort of a more general introduction on formalization, and later on, of course, we're going to focus a bit more on Lean itself. And then after the break, Alain will take over. He'll then really show you some, take a step back and really show some Lean basics. Amongst other things, we can calculate and do some little logic, multipliers, and then maybe get to limits, maybe not. We'll see. And that's going to be much more interactive. Although, I mean, please also in this lecture, please stop me if you have any question. I'd be very happy to discuss, right? So it could also become interactive, but that's also a bit up to you. But the second lecture is definitely meant to be quite interactive. Hopefully you're going to type some Lean code yourselves. And then in the afternoon, we just do an exercise session where you can get to work on more Lean exercises. Maybe you will say one or two things, but most of the time, hopefully, you will just work on it by yourself or together in groups, and we'll be around, of course, for help. And then tomorrow we'll again do some more Lean basics. Going to talk about induction, very basic mathematics in some sense, right? Because with Lean you can do very advanced mathematics, but if you start using it, you have to start at basics. So induction, how you can improve things by induction, or I can define things inductively, and also talk about structures, algebraic structures like groups and things like that. And then we wrap things up with again sort of a more general lecture where Alain will tell you where we are and where we are going, right? All right, but now for the introduction. So we're mathematicians, we like proofs, and sometimes we say, ooh, okay, this is a proof, but this is really a rigorous proof, by which we mean maybe it's the same thing but written down with more details. or formal proof. I mean, even in let's say, well, classical pen and paper mathematics, you also see this phrase formal proof. We really, now we formalize a proof, and it can mean many things. It can also mean we really write down lots of details. I'm not going to cheat. I'm really just going to, you just say, yeah, this is cohomology theories are equivalent or whatever, right? Now we actually, actually going to prove it. But in this lecture theories, and if you do formal theorem proving, by formal proof you really mean something. Okay, this is not the definition. I could give a elaborate definition, but I don't want to. So it's more the idea. It's really any logical argument expressed in some logical formalism, precisely justifying every single step. And of course, this is very important that you, even if you say, now I only have to prove that. I want to show that something is larger than 2. I've shown it's larger than 3, hence I'm done. No, then you still have to show that 3 is larger than 2, right? I mean, every single step. So, of course, there will be assistance. If you really, for every tiny little step, you have to prove every detail down to the axioms yourself, then you will never get very far. So, of course, with the software tools available, these, let's say, little things and also bigger things can hopefully be automated for you. But at the end of the day, either the user or together with the underlying technology will make sure that every single step is proven down to the logical formalism you're using. In principle, you can do this on paper. People have done this on paper. Many of the ideas that came out of this are also now used in software, in proof assistance. But of course, if you want to get to modern math or even just non-trivial undergraduate mathematics, you better use computer. So it's this to formalize, let's say, a proof, justifying every single step down to the axioms in your logical formalism. You use a software tool. There's many names. You can call it proof assistant or an interactive theorem prover. So it really assists you with writing the formal proof and also checking that things are okay. Or it's also interactive, as maybe you've already seen, but otherwise we'll definitely see it in the last lecture, that it will provide you with the proof state, what do you know, what needs to be done, and then there can be little tactics or even bigger automation that helps you prove some of these things in just one step. And then it can really be human-computer interaction where you build up this formal proof. Okay, so I already said it. It's a software tool assisting with the formal proof development. So human-machine collaboration, at least at this point. And I can ask, okay, if I now have a piece of mathematics and I want to formalize it, I want to use such proof assistant to interactively develop inside my computer some formal proof, some computer code that should represent formal proof of some mathematical statement. I have to type this in, and usually, still, most of the time, this can take very long. It can be very tedious, although there's automation and all kinds of libraries and help and tactics. In practice, if you have even a semi-easy result, then it could take very long. Of course, things are changing rapidly now. Again, some of the proof steps that you may still have to do today, maybe tomorrow, there's some automation tool that can just do it for you. What's also very popular nowadays is auto formalization tools. I think they're still somewhat in their infancy, but they're also already showing some results. I think Alain, you will talk more about that probably in your last lecture. Where maybe you feed it some PDF and this tool will create make definitions, lemma, theorem statements, and formal proofs, and it will automate all of this. But still, at this point, you cannot expect to just take your PDF of your favorite textbook, even if it's sort of relatively elementary, and then this will be formalized automatically. You will have to do very hard work most of the time yourself. But again, automation is improving, and also libraries are growing because of course, if you want to formalize something, if you want to formalize, let's say, research mathematics, it will probably depend on much undergraduate or graduate mathematics. If that is already there in some formal libraries, you can just start using it. But if it's not there, then obviously if you want to formalize everything, you have to step down and do basic definitions in your field if those things were not already formalized. So building on already known formalization of, let's say, basic math or also more advanced math can obviously also help to speed up writing, creating some formal proof. On the other hand, one of the, well, not the only reason we get into that, but one of sort of the obvious reasons why you want to formalize things would be certainty that you really know with much more order of magnitude certainty that you haven't made some small mistake, that you haven't forgotten some corner case, that all the definitions work okay together. So the computer can check that your formal proof is correct, and that well, usually again is very fast. So maybe you spent a year trying to formalize some proof of your favorite mathematical area, and then if the proof is not maybe not too computational, or if there are no other let's say issues with crazy type class inference searches or whatever, there can be all kinds of issues. But if it's well, it's almost tautology. If there are no issues, then it's fine, right? But well, with lots of mathematics in practice, can take very long to formalize, and then just the computer can just check it in a matter of seconds or even faster. Just really say, it completely automatically checks that everything is fine. You can be very, very certain that things are correct. Okay, so why do we care about formalization? So some merits of digitized formal mathematics. So this, of course, we're talking about proofs, but it's not only proofs. It's also just making formal definitions. What do you really mean? And if you have this in one big library, maybe if you look at the literature and your favorite object there might be several definitions. Maybe they're equivalent. Okay, then that's not really an issue. But maybe they're not exactly equivalent. Maybe there's some corner cases in which the definitions differ. And then if you, then that could actually create a problem if you're not a domain expert and then use a definition and some statement, and then actually you use it in different context. So you really create, if you have everything in one library, you really create an unambiguous library of results. There can be no misinterpretation of definitions. And then accordingly the theorem statements and their proofs. And if you formalize this and you let the computer check it down to the axioms, then I would say that this will give you very high trustworthiness. I won't say that it will give you absolute certainty. Maybe such a thing doesn't exist even, but of course you're always trusting something. Trusting in your computer, maybe you trusted that no bit flip, you trust your own brain, etc. So, but I think that's it will, whatever this means, it will give very, very high trustworthiness, orders of magnitude more than if you're careful on paper with the proof. And again, this is unambiguous library. And even without proofs, it could be interesting to do this, just to state very precisely what you mean, make definitions of advanced mathematical objects, and state theorems about them. But there's much more reasons why we should care about formalization. It can also lead to new proofs, for example. Because if you're forced to formalize something, usually it's not that you just have your pen and paper proof or your PDF, and here you have your computer, you just start typing, and then no. Usually you really have to rethink the structure of the proof. You have to rethink your definitions, and that can really help you understand the proof better or in a different way. Maybe you come up with once you start chopping your proof up in smaller pieces, which is usually part of a formalization project, then sometimes you encounter necessity to make new definitions, and that those definitions might actually make sense and be interesting outside of this proof. So can really lead to new ideas, new proofs, new concepts, new definitions. I think for example the four-color theorem in graph theory was formalized by Gomche, and then he also realized that certain definitions were very important, and some properties were very important, and they they also turned out to be very useful outside of this formalization project. Well, you can study proofs. Of course, you can also study proofs without formalization. But if you have your proofs in a digital form, then studying the proofs, for example, checking what happens if you modify or remove an assumption, then you can immediately see what happens. For example, if you have some statement and you ask yourself, oh, I had the assumption that my ring was Noetherian. Do I really need it? Okay, and then you can just, of course, in a paper proof, you can also ask this question, and then you go line by line and check where you used it. And you have to be very careful because maybe you actually used it implicitly somewhere. So you have to be very careful and check, go through the whole proof and check where you use it. And maybe that's possible. Maybe in some cases that's not hard, but in other cases, especially if it's a very long proof or very complicated proof with lots of implicit arguments, then this might be difficult or time consuming at least. And in the proof system, you can just remove your assumption, and then the computer just goes through the proof and just points to the places where your proof might break, or where it breaks. And maybe it doesn't break. And they say, okay, I can just remove the assumption. What's probably in the longer proof will happen is that it points you to some places where now the proof breaks, and then you can inspect that and say, okay, do I just need another argument, or do I really need this assumption, or maybe I need something, but I can use something much weaker. But you can immediately get pointed to the places where you have to inspect your proof, and then check what happens. So that's one example. Well, proof automation, already talked about it a little bit. Well, some very easy mathematics is not automated yet, but other mathematics, other types of mathematics can already be automated. That you say, okay, now prove this for me. Just maybe it's even a very easy lemma, but if you have your big digital library of results, it can, for example, simply search the whole library. Right? And maybe you're trying to prove an easy lemma in a domain where you're not really an expert in. And they say, okay, maybe this just follows from two lemmas, but I don't really know the area. And they go, okay, just search the library and see if two lemmas will give me this is the thing I want. And then, maybe if you're lucky, if it's really that easy, then you have a big chance that the computer will find this. But more seriously, it can try to come up with longer chains of reasoning and prove what you want. Again, I think Alain will talk about that more in his last lecture. Again, it's still at the current state is that don't expect magic from this. I mean, if you write down something hard, there's big chance that proof automation will not work. But it's a very active area of research, so who knows what will happen in a few years. And of course, there are also examples, let's say more spectacular examples where it did work. Another reason, if you're interested in AI, so automation, maybe you immediately think of AI, generative AI, but there's also, let's say, all kinds of symbolic methods that are already around for years, for decades, that can help in automating just some algorithms or other good old AI. But well, definitely, if you combine this also with LLMs and stuff like that, you can maybe train AI on mathematics. Of course, you can try to train AI on PDFs or on the archive, but it's still quite imprecise. So if you have a very precise digitized form of mathematics, like you would have if you formalize mathematics, then this is very good for AI to train on. So if you want that computer helps you more with proof automation, you better train it more. So you better have more non-trivial mathematics formalized. And if it's, well, ideally, if you ask, let's say, some generative AI to produce some mathematics for you, then ideally it's trained so well with respect to some formalization language like Lean, that it can also output the mathematics in Lean. And that would be very, very worthwhile, because then you can, for example, detect hallucination very easily. Because now, if I ask generative AI some mathematical question, okay, maybe if I'm asking the question in my field of expertise, I can very quickly check if it's nonsense or not. But if it's a bit outside of my expertise, and there's some subtlety, I might not spot it, and then I'm always like, okay, does it hallucinate or not? But if it actually could also translate this to some formalized mathematics, then it can be checked. Yeah, does it actually make sense? Is this actually correct? You can detect hallucination, or the other way around. Say, okay, the mathematics that has been produced has been formally verified, so I don't have to worry. I can trust it, not just random nonsense from stochastic parrots. And then, well, this is definitely not the last merit. This is the last one on the slide. The more reasons why formalization is interesting. But another thing is that it's fairly easy to do large-scale collaboration on mathematics. I think again, Alain will show you some example of a big blueprint. So if you want to do a big formalization project, you can chop it up in all kinds of little lemmas and definitions and theorems, and then well, of course, make some graph how everything is connected, and then someone can just work on an isolated piece, and if it's done and it's completely checked, then others don't have to worry that, even don't have to understand that that's a part of mathematics, but say, okay, we trust it because the computer trusts it, and we also trust, maybe you claim, oh, this lemma and that lemma will apply that, and of course you can also prove that in detail and formalize it. And if the computer says that's okay, then you don't have to worry like, oh, was there maybe a slight mismatch in definitions, or was there do these things really imply that, or is there some corner case or missing? So you can really chop it up in all kinds of pieces, which of course you can also do with paper math, but you can really just then, not worry about, if somebody claims that the piece is correct, you don't have to worry that it's correct. You don't have to understand it. I mean, it would be nice to understand it maybe, but if you care about the proof being complete, you can say, okay, I understand maybe the overall picture in this technical piece, it's apparently fine, and you don't have to worry about how everything connects. Again, it's nice to have an overview, but you don't have to worry about, oh, am I missing some corner cases or whatever. And there are really examples of many people collaborating on this project. So now, of course, this course will be about lean much more, but again, this introduction is more general. So let me tell you a bit about other proof assistants than just lean. Some people call it the zoo of systems. So some early history of proof assistants. Well, one of the first, I mean, there have been other things around, but one of the most well-known first proof assistants is Automat, created in the late 60s by Nicolas de Bruin from the Netherlands. And well, around the same time, another proof assistant, Mizar, was being developed by Tulecz in Poland. And I've been told that, well, these developments were done sort of, independently, mostly independently of each other, presumably because of the Iron Curtain that was there still there. So largely developed independently. But also the interesting point is that they were both developed by a former mathematicians. Bruin, Tulecz was some topologist. Bruin did some many things. But they were developed by mathematics, and also it was also really meant for mathematicians to use. At that time, I don't think many mathematicians jumped on it because there were many reasons, but maybe one of the reasons was that it was very hard to do non-trivial things with it. But for example, in Automat, some complete textbook on the foundations of analysis was formalized by some student, PhD student. Automat is not in use anymore, but definitely the ideas of development have contributed to modern developments. Both in the practice of proof assistance, but also in the theory with respect to type theory that's being used, etc. Mizar, it's actually still around. There's still some people actually using and developing it. So initially it was a mathematical thing, but then later on, formal verification moved much more towards computer science. I don't want to claim that no mathematicians were involved, but it became, let's say, mostly a computer science thing. where you can do software verification. If you have a self-driving vehicle, it would be nice to know that the software doesn't miss some corner cases. And also NASA already used this for a long time for certain software in space missions. And then, well, past few years, or maybe already the last decade, definitely more and more mathematicians became involved in formalization. And nowadays, it's not just this very small niche thing for mathematicians, but it's actually becoming, well, already has become a bit of a hot topic. Now there's if you do different proof assistants in the zoo, then you actually have to choose a logical foundation. So what I mean, if you want to do something, prove something down, do some axioms using some logic, then you actually have to say what this is. And maybe as an everyday working mathematician, you or at least I used to not really worry about it. I mean, if somebody really pressed me and said, ZFC, everything ZFC, probably, okay, maybe if I do some fancy algebraic geometry, maybe, I don't know, I need some big universes or some large cardinals or whatever, but probably they're not really necessary, but I don't know, but bit hand wavy, and you would just go on and do your mathematics. And one reason is, of course, that you're not, well, maybe for some mathematics, but most of the sort of the daily mathematics, you're not really, your nose is not into the foundations or into the axioms. They're not staring you in the face all the time. But with these proof assistants, you actually get much closer to, if you use it, you get much closer to the underlying foundations you have to take them into account. But if we go back to set theory, so this Mizar is basically set theory. I think it's, well, together with the Tarski-Grothendieck axioms about large universes, etc., and then inaccessible cardinals. I don't know I also get the details, but you can look it up on Wikipedia. But it's basically set theory on steroids, Mizar. And then there's also MetaMath, another proof assistant, which is much more flexible, but there's a large library based on also that set theory. So this is a very large database. And then you can also do type theory. So lots of proof assistants use type theory, where maybe not every, but things have a certain type. So you can say, okay, this is the number 3 has the type of natural numbers. Or maybe I mean something different. I mean the number 3 as an integer, and that's a different type. We'll get into that in more detail later. And then you can do what's called simple type theory. And then there are examples of proof assistants that are also still in use. Whole Light or Isabelle Hall. For example, if you're interested in doing complex analysis, then this is very advanced. And then you can do something called dependent type theory, which is, in some sense, much more expressive and a bit closer to how we usually like to think or develop modern mathematics. And then you get into proof assistants like ACTA, also Lean, and ROC, formerly known as COC. And they're really different logical foundations. But let's say the foundations, for example, Lean and ROC are very close. So now, before we get to the modern age, if you go back, let's say 10 years, I don't know, maybe when that's even before 2015. Let's go back. Oh, that's here. There's some spelling errors in your novel. Shall I correct them? Okay, yeah. So let's say by 2015 or so, or even 14, if you say, okay, what are the sort of the really big formalization projects that have been successfully carried out? Well, of course, maybe different people have different opinions, but you could look at this as some people call this the big 4. 10 years ago. So one thing that was formalized was the Phi-Thompson theorem. Every finite group of odd order is solvable. It's theoretical result in group theory from, I think, the 60s. That I think it was one of the first papers in group theory that was not just very short, but was quite long, and but it's purely theoretical, and it's very important if you want to do classification of finite simple groups. then this is a cornerstone result for it. And this whole proof has, so this is also kinds of algebra, representation theory, and Galois theory. This was completely formalized by a big group of, well, back then was called Koch users by Conche and many others in 2013. So it was a major accomplishment, big formalization project. And then there's also a project of somewhat different nature, the Kepler conjecture. Well, it was first proved and published by Hales, I think together with Ferguson. But in the annals, but the referees said, well, we cannot quite be certain it's correct. It's probably correct. And this was not something Hales really liked. So he said, okay, let's now go and formalize everything. So he started the fly stack project and he formalized the whole proof. So the proof is it's about sphere packings in Euclidean 3 space. So what's the densest way you can pack equal radii spheres in R3? And well, can cover at most pi over square root 18 of space. And it's, for example, attained by actually some lattice packings. And the whole problem is that you want to do all sphere packings, not just restrict to lattice packings. But the optimum is still attained at some regular lattice packings. FCC, and there's some other lattice packing that does it. And how you pile up these cannonballs. This will cover about 74% of Euclidean space if you extend it in the limit. And this is, well, apart from, of course, all kinds of theoretical advances, this is also as a large computational component. This was also one of the problems sort of with checking if the original proof is correct. All kinds of non-trivial linear programming issues to be proven, and there are also all kinds of non-linear inequalities that can be very subtle to check. But ultimately, he managed to formalize all of this, and then it really was a second generation proof. It was not like, oh, I had my original proof where there was some doubt, and now I translated it all and look, it was all fine after all. No, it really became a second generation proof. I really had to look back at the proof and indeed found some small but not non-fatal mistakes. Maybe some cases were indeed missed, and maybe some symmetry arguments were not quite okay. Maybe some other arguments could be improved. So it really became, I really found some small errors, but it's not just about finding some small errors and fixing them, but also really having a much better understanding of the proofs and the concepts. So really the proof got much improved also. Maybe for the fun of it, this is a formal statement. Now this is not to scare you. This just means that they only use old-fashioned ASCII characters. I mean, of course, it's just about typesetting. We can typeset it this much nicer if you wish. So this exclamation mark is for all or something. Okay. So this says, okay, for all packing phi, and of course this is not complete without going through all the definitions, because okay, what's a packing? On the packing, I think it's just a subset of R3 containing the midpoints of the spheres, because you can say, okay, well, instead of looking at spheres, you can just look at midpoints of spheres, and if maybe the sphere should have radius 1, and then if the spheres do not overlap, then the midpoint should be at least 2 apart. So then, if you go and look at this, and I actually didn't check, but probably the definition is just okay. Some subset of R3 where 2 distinct points have a distance of at least 2. Okay, and then I said, okay, for all these packings, there exists some constant which is just gonna play some role in some limit, such that for all radii, if this except for if things are too small, if the radius is at least 1, then if you count, because we're not really gonna do some integration on some part, but what's covered by the spheres, but we're just gonna count how many midpoints are in some bigger sphere. We're gonna intersect this packing set, the midpoints, with the ball of midpoint 0, radius r. And then we're going to count how many midpoints are there in this ball, and that should be at most pi r cubed divided by square root 18 plus some error term. So actually, this is a stronger statement than just saying this is the density. It actually has some more explicit error term, but that just comes out of the proof. It would be on paper. It would also be more annoying to take care of this error term, but by doing the proof, you get this. And I've been told that you can even make this C more explicit, though. You can pull it out of the existence, but that's fine. So again, we can also just use different notation nowadays and write this more closer to how you would write mathematics. Not just using very basic ASCII characters, but some things that are interesting to see is this ampersand before this one says, well, this R is actually a real number and this one is a natural number. You cannot compare them. That's type theory. So this means, oh, I actually cast this one into the reals. So now I can compare this to this real number R. And the same is happening here because this is a real number. Well, the square root of the real number 18. And this is some real number. And you compare it to some integer or some natural number, but that should be casted into the reals. So you have to be precise because you're using different types. Now, also that can become very annoying, of course. Of course, I mean, it is a real number. This one is the real number one, not the natural number one. It's apparently different things for something different. And the systems can also take care of this automatically. But it's good to know that under the hood, these differences are there. And sometimes it's actually very important to distinguish these things. Of course, here it's just annoying. I don't want to type this. And again, for example, in Lean and in other systems, this can be taken care of automatically. And of course, also in this system, system could easily be extended so that this would not have been necessary. Okay, so those were two very big math projects. Maybe the third one will be the implementation of the four-color theorem, also by Conche. But also on the CS side, big things happened or are still happening. For example, verification of the C compiler CompSearch, was done in COC then, 2008, and that is still being updated. So, of course, if you want to trust all kinds of things you're doing, and if you're writing a program and compile it, then you better want to be certain the compiler is working according to your specifications. And of course, you can go further and say, well, I mean, everything operates on my laptop, and this laptop has some operating system. And then, so for the microkernel of some operating system, cell 4, also the specifications were completely formalized this time in proof system Isabelle 2009, and that's also still being updated, if I understand correctly. Okay, so some examples. So I personally like this example of that you using formalization, you find some mistake and you actually improve things. So this was done there's a paper called quality version of the Morse lemma. And the slides will be available. You can even, I think, click it and then we get to some paper, but how do I get back? But one of the things said, okay, abstract. So there was a paper by Sure about some qualitative version of the Morse lemma. I mean, you don't have to understand what this means. If you're interested, you can read the paper. Some of the quality that people care about growth of hyperbolic space. And then Sebastian Guzel was interested in it and tried to formalize this paper and especially this bound. And then he actually, at some point, he stumbled upon some mistake. So he writes, there's a gap in the proof of the main theorem of this article. Okay, sure. On optimal bounds for the Morse lemma, growth of hyperbolic spaces. And we correct this graph, this gap, formalize it in Isabelle 2019, showing that the main theorem is true. We also describe the computer certification of this result. So, so the math was, what happened? Okay, and I think that there was just some inequality flipped. I mean, this can happen. I mean, people have looked at it, has been peer reviewed, etc. But yeah, it's just some tiny little thing happening somewhere. People simply miss it, which is normal. I mean, that I think happens all over the literature. And then apparently there's just some gap somewhere. And I think it's a funny instance of a sort of a medium error, because sometimes, of course, in mathematics you have all kinds of small mistakes, which are just local mistakes which you can fix. Like, oh yeah, I don't know. You can think of your own examples, but just it should be there was a greater equal, but it should be greater, but actually for the rest of the argument doesn't matter, and stuff like that. Or just simple, little isolated things, typos or slightly word things that can just be locally fixed. Of course, there can also be a major thing where everything breaks apart, but this, if I understand correctly, was more of an intermediate thing that really was non-trivial to fix. Not that you just flip the side and everything works. They really had to work, but then they could fix the proof. But what's maybe even more interesting, and then Sebastian could formalize everything, is that this is about some precise inequality with some constants, and then by using this proof assistant, it was possible to really do the bookkeeping of all the constants involved in all the inequalities, and get some stronger result than you would normally do on paper, because it's very easy to keep track of all the details and all the constants, and if you change something, then again studying proofs becomes much easier with the proof assistant. You immediately see, does this work or does the proof break, and if it breaks, oh, maybe I can fix it here, I can fix it there. So you can really much more easy optimize your proof if you're interested about some optimal constants, and at the same time also be certain that everything stays correct, that you haven't forgotten some piece where it maybe doesn't work. So I like this example, finding a mistake, fixing it, and then because of formalization, and then also using formalization to actually get a very much stronger, nice result. Okay, so maybe I should be a bit quick with that. Well, there are many formalization projects, again, also in different proof assistants, but let's focus on Lean a bit. Okay, so this is some advertisement, the big capset problem. Did several years ago together with Johannes Holsel and Rob Lewis. So it's some extreme combinatorics problem where you have to bound the size of a capset, focused in annals. And then we set out to formalize this. One of the reasons was, well, it's an interesting result, but also at that time there wasn't much linear algebra in the mathematical library of Lean, so it was a good reason to develop more linear algebra. And also, as what I think was fun of this formalizing this is that we also improved on the proof. First, we just improved on the proof, simplified it, and then with one of the authors, we even the original authors, we even simplified the proof more. And again, in theory, this could have happened without using a proof assistant and just do it on paper. But really, because of the whole formalization project, there was sort of a need to simplify, or we also pointed to naturally to places where to simplify. And there's basically two steps in the proof. And the first step we very close to just the original paper, but the second step has been simplified a lot. So I don't want to go into detail of all the mathematics involved, but the slides will be available and you can click them and then read more about this and also about the Lean code. And then, the nature of liquid vector spaces. There was some challenge by Scholze, and then Alain, you will say more about this in final lecture. But some big challenge, very advanced modern mathematics. And Scholze said, okay, can you formalize this? And then a big team led by Commelin, Topaz, involving many others, spent some time really formalizing the statement and the proof of some key results of liquid vector spaces. And it's Vrije version, so it's not just algebra, combinatorics, but you can also do things in topology, geometry. That was one of the points Patrick Massel wanted to make, and together with Oliver Nash and Floris van Doorn, he formalized the sphere inversion. So I won't show you the video now, but you can maybe you've seen it. You can turn the tooth sphere inside out in a continuous way. It has to self-intersect, but without creating singularities. So that's a nice result from geometry. There's the H principle is involved, if that means anything to you. But this project really showed that those kind of geometric analytic statements well, can also be formalized. And again, I mean, if you're interested later, I mean, you can click links in the slide or I can show it to you later. And then there's also the polynomial Feynman-Russell conjecture. Tao and many others proved some famous conjecture, and then Tao said, okay, let's formalize this, and then lots of people in the Lean community jumped in and said, oh yeah, that sounds like a nice idea, and then within a month or so, do you remember? Yeah, lots of people just formalize this complete paper way before it was refereed, and also I think they extended it and optimized some things. And there are much more papers and projects, also ongoing projects, finished projects at the Lean community page. So definitely take a look at that. So very important if you want to develop mathematics and do these formalization projects, that you rely on some library. You don't want to start proving very basic results from scratch. I mean, it's not like, oh, now we have to define a ring and basic properties of a ring. Like, oh, and if you do elliptic curves, it's nice that if the curve is defined. So some of the basic properties actually we need much more in the library, but okay. So for Lean, there's one big. So every proof assistant has its own library, or sometimes libraries. Well, Lean's viewpoint is that basically there's one monolithic library of mathematical results. Of course, you can create your own libraries, but there's one big library called MATLib that hence is also very interoperable. Everything, can be connected to other mathematics. The definitions align, and you can build on this library if you do a more advanced project, and also of course vice versa. If you do some formalization project, then maybe you encounter missing pieces and you can contribute back to the library, or maybe just the thing you want to formalize is very interesting, and maybe you want to have that in MATLib. Although I have to warn you that MATLib, it's not just that it accepts any mathematics. It really wants to be very general for one thing. So if you have a very specific result, they might complain like, well, that's interesting, but it's not in sort of the most general shape, although maybe the most general shape doesn't really exist, but it's not general enough. Let's put it that way. But you can still, of course, use it and maybe have parts of your project in MATLib. So let me maybe click a few things. So let's go to some overview. Maybe I don't want to go through all the details. You will also talk more about MATLib.
Yes.
So
We'll show an example.
Okay. So if you're interested, you can go through this. Like, there's lots of general algebra, category theory, group theory, all kind of things. Ring theory, field theory, even some homological algebra, etc. Well, linear algebra, topology, analysis. Then the list goes on. So have a look at it in your own time, maybe, if you're interested. Maybe show some statistics. Okay, so we're now in 2003. There was a major version bump from Lean version 3 went to Lean version 4, and also the corresponding mathematical library to be ported from MATLib 3 to MATLib 4. So we're now at MATLib 4. And at some points things got ported, and almost everything got ported, and then now we're just building MATLib 4, which contains over 100,000 definitions and lots of theorems. But theorems, I mean, every statement with a proof is called a theorem. I think in this, I mean, you can call them lemmas in the library, but I think this counts everything that's the statement that has a proof. There's also things that are called lemmas. So pretty sure that the lemma 1 + 1 = 2 is also in the library. So these are not all deep results, but some results are definitely very deep. And then the hundreds of contributors. And again, Alan will say more about this. Maybe what's nice to show is the dependency graph, also called the import graph. All right. So this really shows how mathematics is connected. This is you have your algebra here, and then where's analysis, and well, category theory. I think it used to be the case that there was a big chunk and then a little island with almost no connections to the rest of that island was category theory. But nowadays, well, so all the nodes are represent some file, and then they're connected if one imports the other, if one uses the other. So you can really see that mathematics is as a whole is connected, and then you have connections between algebra and analysis and number theory and well even category theory. And yeah, if you find this fun, you can play with it. You can click on some file. Ooh, project spaces. Okay, maybe click on it. They say, okay, what's that about? This clause is separated. Ooh, okay. You can play around with it. So maybe my final 2 slides, I want to show you a little bit of the type theory of lean. So this is in some sense basic lean, but then after that we take a step back, and then in the second hour then we'll do some other basic lean code. And actually, to be honest, you don't really have to understand the underlying type theory to do basic formalization. You could, if you want, just ignore it. But if you do more advanced things, it's nice to know. Well, could be handy. And at the end of the day, we're mathematicians. I think it's also nice to understand a bit what's actually happening under the hood. This will be very brief anyway. Is this readable? Maybe I should enlarge it a bit. Is this readable? Okay. So now I do something that apparently is bad. I import the whole library, and because my laptop is fast enough, it's not really complaining. But Alain pointed out to me that's from educational perspective, it may be well. Okay, there are different reasons why you do not want to do this. And the most pragmatic one is that if your laptop is not, your computer's not the fastest, might take some while. But I'm just very lazy in importing the whole library. And then, okay, so lean uses under the hood types, even dependent types. So this means that every term, everything that you can type that has some meaning in lean, that's good syntax, that has some type. And that's actually that's different from, let's say, ZFC set theory, where just everything is a set. Here you shouldn't be allowed to compare things that have a different type. And that's actually much closer, I think, to mathematical intuition. If you ask a mathematician, like, is this matrix representation of the quaternion group equal to the square root of pi? Then I think most mathematicians will just stare at you and say, "Are you nuts? that doesn't make any sense, right?" But actually, in set theory, it's a valid question because everything is a set. You have two things and ask, are these sets the same? And even worse, depending on how you construct your real numbers, the answer could be yes. Yeah? Of course, in practice, this is not really an issue because you forget how the reals are constructed, and this will be not an interesting statement anyway. And people will still say, "I don't want to. This is not the question I'm gonna look into." But the point is that in principle it's a legal question, and even the answer could be yes, depending on your definitions. But the reaction, like, you shouldn't ask this question, this is nonsense, that's of course the normal thing to do. And in type theory, that would be the thing. They say, well, you're asking for an equality between two things of different types. That's not allowed. Yeah? Maybe you can cast one into the other, because if I'm asking, is if I do the natural number 1, I add it to itself, is it equal to the integer 2? And then lean would actually say, well, no, because they have different types, but you can still ask such questions and then say, well, okay, I probably mean that this natural number 2, you can cast it, interpret this as an integer, and then the answer is yes. So sometimes types are different, but then there's a natural casting or a natural embedding of one in the other. But the whole point is that we have types, that every term lives in some type. Every term, every legal thing you can write down has some type. That's usually how we like to think about mathematics. Every term has a type. And now you can, so this is how, so I hope you all installed Lean and have seen these things. You can write Lean code on the left, and again, much more will be done in the next lecture. And you can, for example, say, okay, check, this means ask for type. I type in 2, and it says 2:n, meaning 2 has type natural numbers. Okay, fine. And then just for notation, I open something, and then I can type in pi, and I say, okay, check the type of pi, and this is the output. Pi has type R. So this column is means it has the type. Most of the time, you can just think of this as element containment. But I do want to emphasize that we're not really talking about sets. It's type theory. But for lots, maybe not most, but lots, almost most of practical purposes, you can think of this as in your mental model. You can still think of this as set contained. Pi is contained in the reals, but it's really about types. Pi is pi R. And then luckily you can add pi to I, because I'm allowed to write pi plus I. Check what is the type. Pi plus I is the complex numbers. But now you notice this little arrow, and this little arrow. It's basically just the natural embedding of the reals into the complexes. You say, pi. This arrow pi means I cast pi into the complex numbers. Just think of this as I apply the natural embedding map from R to C. Do it. And it's not complaining. It just says, I want to check this, and you meant this, right? Well, there are other type booleans. True is a boolean. You can define things. You can define a function. Define the function f. I say, okay, I will put in an integer z, and out comes n squared minus 1. And then, for typographical reasons, I put brackets around f. Otherwise, it will just, that's a different thing. Because f is a type z to z. It's a function from the images to the images. You can also do computations. You can evaluate stuff. Evaluate f at 0 or output -1. Yes.
If I want to compare pi to some other, do I have? Is it possible to compute pi or?
Yeah, you can. The pi has all kinds of digits. You can get digits of pi. Yeah, absolutely. Okay, I can have some variables, a natural number. I can say, okay, if I want to introduce some field, talk about the field k, I say, okay, k is some type. Everything is a type. And then say, okay, it has the structure of a field. K is a field. And then here's the example of what dependent means. For example, if I want to talk about vectors, k to the n, then I could model this as, maps from fin n to k. So what's fin n? If you hover over things, it will give you some information. It says that the natural numbers less than some upper bound. This is the natural numbers 0, 1 up to n minus 1. So so this is how you could see vectors in k to the n, just ordered n tuple of elements of k, which you can just model as some map from 0 up to n minus 1 to k. And this depends on n. So this is an example of a dependent type. And then I can still talk about 0, but now this is really the 0 vector. Not the natural number 0, but the 0 vector. Now, since types themselves in Lean are terms, and I will stop. I will try to stop within 5 minutes. Types themselves are terms. Each of these types have a type. The word type, by the way, is completely overloaded in this whole theory. You can say, what's the type of type, and stuff like this. Now I'm going to type, what's the type of type, etc. Okay, so I can check the type of natural numbers, and n, has type. This is column mean. What is the type of n? Well, it's type. Type itself is a term in Lean, and it is a type, just like the natural numbers is a type. Of, for example, 3 is the type, that type, is the type of the natural numbers. Yeah? And same here, but also the complex numbers have type, Booleans have type, functions from Z to Z have type, these, well, K to the N is type. But since types are terms themselves, everything should have a type, so you can check what's the type of type. And then type has type 1, because type actually is type 0. I could add a 0. It starts with 0. I could add a 0, and then if I type 0, it says that, well, it just says type 0 is just type. Type is just syntactic sugar for type 0, and it has type 1. I say, okay, but what's the type of type 1? Well, type 1 has type 2. Yeah. And yeah, what's the type of type 32? Oh, type 32 has type 33, etc. And then you can say, well, what's the type of type 33? Say, oh, well, I don't want to tell you, because this is just like with precision. Eh? Actually, under the hood, it has to stop somewhere. So it stops at type 32. But if you really want, and I don't see any reason why you would, but you can increase the universal level. But in some sense, for most of the practical mathematics that you do, this is abstract nonsense, because almost everything simply lives in type. I mean, there are a few things for which maybe you want to go a little bit higher, but most of normal mathematical objects live in type, or actually below it, that they're theorem statements. So yeah. So you have this infinite hierarchy of types, type 0, type 1, type 2, etc. Well, in theory, it goes on indefinitely, and in practice, if you actually want to do formalization, you have to say, okay, I cut off at type 32, but cutting off at type 3 would also be more than fine, or 2, 1 most of the time. We have prop, and the type of prop is type. So it actually starts, so you have all kinds of other mathematical things, but the main typing hierarchy starts with prop, then you have type, then you have type 1, type 2, type 3, etc. And prop is very important. It's a special type of type. It's where the propositions live, the theorems, the lemmas, etc. So a slogan, which is used in Lean and in other systems to dependent type theory, is that you have propositions as types and proofs as terms. So if you're gonna write down a proposition, theorem or lemma, or how do you call it? Let's say 1 + 1 = 2. I can also check what's the type of this statement. This is just one statement, and it says the statement 1 + 1 = 2 has type prop. So your theorem statements, or completely trivial lemmas, have type prop. It doesn't mean that they're true. I mean, I could also do 1 + 1 = 3. It's just a statement, yeah, just a mathematical statement. I check what's the type of this mathematical statement. It's a proposition. This proposition just happens to be false, because, well, this is really false. You cannot say, you were in the 0 ring. It's true. No. Because it interprets what it means, right? I mean, this is a natural number. Huh? And yeah, and this is the standard natural number addition. Huh? So you can really go through what all the meanings, and then I really mean the natural number 1, the natural number 3, the normal natural number addition, and then it's false. Yeah. But it has a type. It's a proposition, or something like this. Yeah, for all natural numbers x and y, x + y is y + x. Yes, so natural number addition is commutative, sure. But I didn't prove anything. I just say this is a statement. It has type prop. Of course, you can do more interesting statements. I don't want to go into the details of searching for it. I mean, this is actually a statement that's basically in the library. You can find it, but it just says, okay, every natural number can be expressed as a sum of 4 squares. There exists for every natural number n, there exists a, b, c, d, such that the sum of the squares equal to n. And that's a prop. I could also remove one and have the statement every natural number is a sum of 3 squares. Of course, that's not true, but it's still a proposition. Then, I mean, could try and prove it's false. I could try and construct a counterexample. This I can try and prove. Actually, that's already in the library. Yeah? or other things like, oh, if you have a Noetherian ring, then the polynomial is over. This is Noetherian again. Yeah. Well, yes. It's some statement that has its prop. So I don't want to go into the details of searching for it and proving for it. That's really the next lectures. Maybe the final thing I want to say, because I should really stop, is for if you have a proposition P, what is a proof of P? So proof of P is some term, because that's what all the things that are created or that you can write out that makes sense to lead are terms, and then so some proposition. How do you prove it? That's again creating it, because this is a term, this is a term. Then you create another term. You create something using the interactive theorem proving. You create something that makes sense. Call it proof here. That has type P. So if I have some proposition, what does it mean to be correct according to Lean? It means that it finds, you can write down something, some Lean expression that has type the proposition you want to prove. Yeah, so 1 + 1 = 2. If I want to prove it's true, I need to create some expression, some term that has type 1 + 1 = 2. And then you have some funny thing called proof irrelevance that, prop is special in the sense that the propositions, so P in prop, if it's true, it only has one proof. Maybe you can write on all kinds of different proofs, but by definition of the underlying logic, there's proof irrelevance. Two proofs of the same statement, even if they are sort of mathematically different IDs, are considered equal by definition. That's some issue if you want to do homotopy type theory, but you can hack that. But let's not go into the details there. So the final thing is this arrow. So for implication, we use this function arrow. And that's really also how it should be interpreted. This is not just only syntax. Because if you have an implication, so suppose that P and Q are propositions, and you know that P implies Q. You write P arrow Q. And if I suppose it's true, it means I have some term of that type, because that means I have a proof of this thing. And suppose I know that P is true, that means I have some proof, something of type P, I have proof of P. Then what is T P of P? So this just means I apply, this is actually a function. This is a function that takes in a proof of P and outputs a proof of Q. Okay? So the proof of P, well, I assumed I had it, and now I apply T to it. So this is just function application we don't write brackets. So if you apply this function to a proof of P, it means I have something of this type. I apply T, I get something of this type, and indeed, this T of a proof of P will have type Q. In other words, this will be a proof of Q. Yeah. And that's really what this T does. So assuming that you have an implication, P implies Q, really means I have a proof of, if I have a proof of P, I can apply T to it and I get a proof of Q. Yeah. That is completely in line with this interpretation of proofs as terms. And then at the end of the day, what's really happening under the hood, verifying correctness of something. So if you construct it with all your tools, some formal proof, verifying correctness, what's happening under the hood is really just type checking. It says, okay, you want to prove this statement, you supplied some term, one way or the other, you worked years on it, you used all kinds of things, but you have some lead term. I check if this term has type the statement you want to prove. And if it checks that this type is correct, then it says, okay, you have proven, formally proven your statement. So that's really, in some sense, all that's happening all the time is type checking. And not just for natural numbers or other things, but also for proofs of statements. All right, I think I should definitely stop here. Sorry for going over time a bit. Thanks for your attention. And I don't know, do we take questions now? Or
we take questions. There's coffee in the other room. Questions? I have a stupid question. Further up, when you type 1 + 1 = 2, for some reason it gave the value true. And then
sorry.
Sorry, what's
this? Okay, so I didn't explain. This I typed myself.
Okay,
yeah.
okay.
Because I did not introduce you to any of the lean syntax, so it's actually a very good question. I didn't even think about this myself, but this is just a comment. So it doesn't give. I just type this. This is what I type as human. So I also type. I could have typed false here. Yeah, so this is just a comment. I just say, oh, remember, it's Monday morning that 1 + 1 is indeed 2. Yeah. And remember, 1 + 1 for natural numbers is not 3. Yeah? But this I type myself. But lean should get to work to. I mean, this is very easy. I mean, it's trivial to prove for lean, and you can also find that this is false. Let's see, show that this is not false.
Any questions? Or
Yes.
After you take 1 + 1 = 3, and then you have that in proposition, you find in the. Can you use that to prove other things, or does the computer know that false?
So the computer doesn't know anything about it. It just knows that this term has type prom. It's not. It's not a lemma I can use. It's just okay saying this is a term that makes sense. As a term, it's a well-formed statement. The statement is a proposition. But it's not saying anything about being true or false. So I cannot start using this. I mean, if I want, I could write a lemma and say, well, if 1 + 1 = 3, then, well, the Riemann hypothesis is true. Yeah? I could also, just what I can do in practice, if you develop things, you can say, okay, I know this is true, but I don't want to prove it just yet. I can what's called sorrying statement. I can write down a theorem, say, theorem, 1 + 1 = 3, colon equals sorry, meaning I'm not proving it, I'm just using it, and then you can use it later on. But if you do such a sorry, then everything that depends on it will be flagged. Like, well, this depends on something you didn't prove. Yeah.
And if you say 1 + 1 = I, it would just object that it's not a proposition.
Well, we could try. Oh, it's a proposition.
It's a proposition.
Because I'm actually, why are there no errors here? Arrows. I would actually, okay. Maybe I can.
Because it's just a numeral notation. It knows it's
okay.
identity 1. And,
Okay, yeah. So now this one, it's now trying to be smart again. It says this one is of net of red R1. So it's a natural number 1 that you consider as a real, and well, for some reason it didn't give the arrow like it did before. But if you hover over it, you see that it is not just a natural number 1, because if I do the 2 again, and I hover over this 1, okay, then at least it says this is a natural number of net 1. Okay, some blah blah blah, but it's a natural number. So it didn't complain because it knows how to, because it tries to be smart. It knows how to interpret things like that. Sure, you mean the real number. But if I put something different, I mean bool or whatever, if something doesn't make sense, then it just starts complaining. Then it's not a valid lean term anymore.
If I wanted to verify a 0 a natural number, it will say yes.
Yes, yeah.
That would be false.
Yes, I know. I'm also a number theorist, so it needed some getting used to. But yes, in the standard library, 0 is a natural number. Yes. I'm sorry.
The relation between being provable is that provable or provable, or do you think that everything that's provable in linear time in one will be in the other, will have conjecture or no? I mean,
so you're talking.
We have proposition. We know proposition. I mean, of course, because of type dependent, we think that sometimes game is more convenient. But let's have 10 newspapers with people with Isabel proving the same thing. So do we think that everything is provable in reasonable time in one would be provable in reasonable time on the other, or is there a belief about this?
So it's a very good question. I actually don't really know the answer if the systems are too different. But if, for example, if you talk about very closely related systems like lean and rock, I should say, I think say that it's more about the tooling and everything around it. That's a real difference. If you really look at the underlying logical foundations, it's so close that I would have a hard time imagining one thing that's provable in one thing and that's not provable in another. But
that's why I agree with that, because at the beginning when Lean was, people were disclaiming about how it's used, how it's practical to have this dependent time, they were saying, this would be impossible to prove in Isabel or
I think some of the, I mean, if you do, let's say, more classical mathematics, so for example, classical complex analysis, I mean, that's done beautifully in Isabel. So it would take definitely some time. I mean, I'm certain you can do the same thing in Lean. It's more expressive, but sometimes having dependent types also complicate things. For example, some of the automation is much harder if you have dependent types.
Do we have a relation between the best and worst sides of number of complexity? I mean, types of short example that has a very long counted by number of characters, Lean proof and Quark proof or Isabel proof, including the size of the proof itself.
You have to. Okay, so this is it's a subtle question because what are the proofs? Is it just the things you type? Or is it the thing it creates? Because for example, if you look at certain types of automation, you can in Isabel just say, okay, by sledgehammer, and that's some fantastic automation tool. And then certainly, okay, I don't know, I can give you immediately an example, but I can certain that there are examples that are just, let's say, a one-liner with automation there that will take many lines in Lean still. Of course, the point is that the automation tools for Lean are still improving, so maybe a year from now or 10 years from now, this is not the case. But at this point, there's certainly all kinds of proofs that for which, let's say, in Isabel, some automation tools can do them immediately. And in Lean,
I'm checking my clock. I mean, there is CPU clock, and the instance that does have this, so I don't care about what it does. I care about the number of flips and
okay, well, I mean, the point is that the automation, for some of these things, the automation tools are simply not there in Lean, so you have to type it in as a human. So so what does then CPU time mean? I mean, at the end of the day, if both systems can automate it, okay, then maybe you can compare CPU time. But usually the automation is so different that the things that can be automated here are maybe not yet automatable there. You can talk about another thing that's checking if the proof is correct. Okay, that's all automatic, but then you can also compare CPU times, but I think that's maybe less.
I was saying that fine because I was not so much. I know that different ones would give different results, but I was curious about if we can compare them and translate what.
Well, translation is very, very hard. I mean, people. Of course, this will be very nice because, of course, if some big theory has been set up in, let's say rock. You want to have it in Lean. It's not really interesting. Maybe you want it, but it's not really. That's been done. People have thought about this, and this actually happens often. Some manual porting. That, for example, in Isabel, doing limits by using filters worked fantastically. And then the guy who actually did it in Isabel just translated it to Lean, and then we had it in Lean, right? But it's very useful, but it's maybe from a scientific point of view, it's more engineering. So having automatic translation tools will be fantastic, but it turns out to be extremely hard, even for systems with very close logics like Rock and Lean. Even porting from Lean 3 to Lean 4, it's just a version update. It was at the end of the day, people automated, well, not everything, but a big chunk of it. But it was a major project. Just porting it within the same system to one version update. So it would be nice to have, but it's apparently is a very hard and difficult problem to translate. But maybe LLMs can help. I don't know. You can say that about everything, right? But we don't know.
So I say we can continue the discussion over coffee. Shall we?
Yes.
Shall we come back in half an hour and chop a bit off the lunch break? Does that make sense? Yeah. Half an hour. So
I'll make it 25.
30, so 5 to then, is it? We come back at 5 to 12 and then take the day off.